In this video, I'm going to go over a transportation problem. In particular, I'm going to introduce a transportation problem description, translate that written description to a linear programming model, and then show two different formats of that particular LP model. So the problem that we're going to use is adapted from the Winston text. For those of you that do not have the Winston text, we're including here for completeness. So reading through this, a company supplies goods to customers who each require 30 units. So you can say each customer demands 30 units. The company has warehouses. Warehouse 1 has 70 units available, and the remaining warehouses each have 50 units available. You can think of this as the supply of my warehouses. The per unit cost of shipping goods from warehouse to customer are shown in the following table. So here I have a table. Interpreting this table, you first notice I have 4 warehouses and 6 customers. I have a cost associated with shipping between each warehouse and customer pair. So for example, taking the first one, the cost to ship from warehouse 1 to customer 1 is 15. It's a per unit cost. Or similarly, the cost to ship from 3 to 5 is 25 per unit. And what we're asking with this problem is how much should the company ship out of each warehouse to each customer such that they minimize cost. So this last sentence is going to give us a lot of detail about our decision variables and our objective function, and all of the other text is going to give us idea about the constraints that we need. So first I have a visualization of this particular problem, and so here I'm going to move this right there. And I have depicted this problem. I have a set of 4 warehouses. Associated with each warehouse is the supply. So I have interpreted from the text that warehouse 1 has a supply of 70 and the other 3 have a supply of 50. And then similarly, I have 6 customers and each of my customers demand 30 units total. And I can ship between each warehouse and each customer. So I have depicted here, or illustrated, an arc between warehouse 1 and each of the customers. Associated with each arc is a cost that I've pulled from the table. So here, this table has told me that the cost from warehouse 1 to customer 1 is 15, and I've placed that along each of the arcs. What I have not illustrated here is all of the arcs out of warehouse 2, warehouse 3, and warehouse 4. And so there are 6 arcs out of warehouse 2 going to each of the customers, and they each have their own cost, and that's coming from row 2 of this table, or this row here associated with warehouse 2. And then the same for 3 and 4, and the costs are pulled from this particular table. But for cleanliness, I've just used this 3 dots and just shown the arcs out of warehouse 1. And so what we're asking here is to first translate this written description to an LP model. And so I have stuff written out that I'm just going to reveal. And so first we need to determine what our decision variables are going to be, how we're going to define them. And so in this particular Sorry, it just zoomed out. Let me just zoom back in. In this particular problem, if we think about, okay, that's probably a good, sorry about that, zooming out and in, but we need to determine our LP formulation. We need to determine our decision variables, and according to this last sentence, we need to determine how much the company should ship out of each warehouse and to each customer. So I'm going to define here decision variable xij to be the number of units shipped from warehouse I to customer j. And so I write this out, for example, if you are struggling with notation here, I have x11 is the number of units shipped from warehouse 1 to customer 1, so that there. And similarly, x12 is the amount shipped from warehouse 1 to customer 2, so on and so forth, all out of warehouse 1. I also have x21, 22, so on and so forth for everything out of warehouse 2, also for out of 3 and out of 4. So I have 4 warehouses, 6 customers for a total of 24 decision variables. Next, I need to determine what my parameters or constants are going to be associated with this problem. And so here I am going to define M as my number of warehouses. For this particular example, I have 4 warehouses, so M is going to equal 4. I'm going to define here N as my number of customers, so in our example, N equals 6. I'm also going to define a cost to ship from each warehouse to each customer and denote that Cij for every ij pair. And so here there's going to be 24 Cijs, which are directly populated from this table. Next, I know I have supplies associated with my warehouses, and that is for each warehouse I. So for I equals 1 to M, where here M is 4. And I also know I have a demand associated with each customer, so denote that DJ, and that's for each J 1 to N, where N here is 6. So there are the parameters associated with them, and I can pull the actual values of these based off of my description from my supplies, demands, and this cost table. Next, I need to start marching through and defining my objective function and my constraints. So first I'm going to write this out longhand, and then we're going to do summation notation for this next model. So first, I need my objective function. And so according to my description, I want to minimize the cost of shipping from each warehouse to each customer. And so I know that this table gives me a per unit cost. I know my decision variables capture how many units I'm going to be shipping along each of these arcs. And so how I get the cost is I just multiply that cost times how many I am shipping, and I want to minimize that. So all I've done is I've listed out, this is the cost out of warehouse 1, 2, 3, and 4. And so this 15 is pulled directly from this table. You can see it's 15 to ship from warehouse 1 to 1 times the amount I ship from warehouse 1 to customer 1. Or similarly, you can go through this, the amounts that you ship from 2 to 6. So this is warehouse 2 to ship, 2 to 6. And it has a cost of 45 times the amount I do that, so which is x26. And so you can see here already, as you would increase the number of warehouses and the number of customers, this is going to be tedious to write out longhand, and so that's what we get to in our next formulation here, where we're going to use my indices and sum over warehouses and customers. So next, if I think about what constraints I need, I know that I have set supplies and I have set demands, and so I cannot ship more than my supply out of this warehouse and for each of my warehouses. And also I know that I want to meet the demand of each of my customers. I want them to stay on as customers, and so I need to ensure that the amount I ship from my warehouses to each of my customers meets or exceeds the demand that they want. And so with that, I'm going to take first the supply, and then we'll get to the demand. So first I have a supply constraint. And what I'm saying is the amount I ship out of warehouse 1, so I can ship to customer 1, customer 2, 3, 4, 5, 6, all from warehouse 1, so you'll see that the first subscript, the I subscript, is the same here just for warehouse 1, and that has to be less than or equal to 70. I write this constraint out for each of my other warehouses, so I have 4 warehouses total. I should have 4 supply constraints. And what you see here is, so for warehouse 2, is all I'm doing is I'm saying that the amount I ship out of warehouse 2 has to be less than or equal to 50, its supply. Same for 3 and same for 4. So the only thing changing between these constraints is the first subscript, or that I subscript in my Xij. So this captures my supply constraints, and now I need to get to my demand constraints. So I am going to have a demand, and I need to ensure that what I ship to my customer meets or exceeds its demand. So for the first customer, it has a demand of 30, and the amount you ship from warehouse 1 to customer 1 plus 2 to 1, 3 to 1, and 4 to 1 has to be greater or equal to 30, which is exactly what we've written out here. And I need to do this for all of my customers. And so I have 6 customers, so I should have 6 constraints. I list on the right-hand side their demands, so all of my demands are equal. And I sum over each of the warehouses and how much they're shipping to that customer. So in contrast to the supply constraint, the demand constraints have the second subscript, or the Xij. So the J subscript is the same across each of the constraints, and it's changing, and you're summing over my different warehouses. So here, this last constraint, my 6 is staying the same. That's the amount I ship to customer 6, and I'm summing over the amount I ship from warehouse 1, 2, 3, and 4. The last thing I need that's very important that you should not forget is non-negativity for my model. And this is just saying for all of my 24 decision variables, I cannot ship a negative amount from a warehouse to a customer. So as I mentioned before, and as you see now with our full LP model, this would become very tedious and not fun to write out as you increase the number of warehouses and the number of customers. And so what we do is we've defined some notation or parameters up here, both our decision variables and our constants. And so what we're going to do is we're going to use that to condense this LP model and use summation notation. And so that's what we're doing for the second part here. And we're going to start with our objective function. And so our objective function, here we summed over every warehouse. So you can see there's 4 rows, and that's a warehouse. And within that, I summed over each customer. So I'm summing over every warehouse. So I equals 1 to m. So m was here was 4. J equals 1 to n. N was 6 for our example. And I multiplied the cost to ship along that particular arc times the amount I shipped on that arc. So Cij times Xij for every pair of Xij. And so this is much more condensed than this. And as you increase, it's much nicer to have this particular notation. And they are equivalent once you define that Cij is exactly this table. Next, I have my supply constraints. And so with this, I know I have a supply constraint for each of my warehouses. So if you look that there's 4 constraints, it's 1 for each warehouse, and so you can get that I is staying the same here within a particular constraint, and I'm summing over J. So it's for each warehouse, and I'm summing over all of my customers, and I'm saying how much am I shipping out of this warehouse, and summing over all my customers, and that has to be less than or equal to the supply I have available for that set warehouse. Next, I have my demand constraints. I know I have a demand constraint for each of my customers. And so here I have n customers, and I'm going to sum over my warehouses. And I'm saying the amount I ship over all warehouses into this set customer has to be greater or equal to the demand for that particular customer. Lastly, we finish with is a non-negativity. And so, I didn't reveal everything. What we're saying here is that all of my decision variables, Xij, for every ij pair has to be greater or equal to 0. And so you can see that this is a much more condensed version of this particular model, and it makes it much cleaner, especially as you increase the number of warehouses and the number of customers. So looking back at what we've done, we have introduced a transportation problem description, translating the written description to an LP model, and shown 2 different formats of the LP model. So this is just an introduction to transportation problems.